All right, next example we have here, example 1, we want to verify Stokes' theorem for the given vector field capital F and for the upper hemisphere of the unit sphere with outward pointing normal vectors. So first thing we can do here is actually sketch this. So let's go ahead and sketch a hemisphere here. Not my best, but whatever. Okay. So z-axis, x-axis, y-axis. This is the unit upper hemisphere, so radius of 1. Okay. And let's go ahead and just say we've got that right there, and then okay. So if we orient this with outward pointing normal vector, so put a little sort of curvature on that. So let's go ahead and say that's our kind of curvature. There's our cylinder, or our sphere. So this vector right here, this is outward. So outward on the upper hemisphere is identical to upward, i.e., the z component of this vector should be non-negative or positive. Okay, contrast this with the lower half, right? If we had the bottom half here, if we took an outward pointing normal vector on the lower half, outward pointing on the bottom half is synonymous with downward, having a z component that is non-positive, right? It's negative. So that's what we want here. So so that's our surface S. We have a normal vector specified, that's this. Now we want to figure out how we should orient the boundary of this. So here's the thing. An orientation for a surface automatically determines an orientation to its boundary. And vice versa. If you specify an orientation to the boundary, then that automatically determines an orientation for the surface. So these two things are linked. They correspond. So we've already been assigned an orientation to the surface. So what orientation does this determine on the boundary here? So the way that we define orientation more generally, actually, is if you orient your surface, S, with a given normal vector, then we determine an orientation for the boundary by choosing a direction. So let's pick a point here on the surface. So pick a point here and consider a path. Like imagine you're an ant on the surface of this hemisphere and you're walking along some path, taking some walk, and then imagine you're going to go outward through, right? So imagine if the ant could fly, it's going to just continue in this direction. So imagine a path exiting, okay, a path exiting. So it could be like this, right? It doesn't matter really, just imagine a path exiting the surface. So at this point, let's just go ahead and say it's right here. So there's our outward pointing trajectory. Now, this vector right here, when you take the cross product of it with, let's say, this vector, so this orientation right here, what do we get? Well, using the right-hand rule, if you put your right hand in front of this computer screen, looking downward, curling your fingers to the right, you should get a vector that's pointing sort of out of screen. Okay? So a lot of times this is denoted like this, because if you imagine somebody shooting an arrow at you, right? Somebody firing a bow like an old-time arrow at you. If you see the arrow coming towards you, all you would see is a little dot. So a lot of times they just do that to denote outward. But if the vector is, or excuse me, if the arrow here is being shot into the screen, what would you see? Well, you'd just see this little tail piece, so you'd see something like this. So a lot of times, we haven't used this in our class, but I know I've used it in physics. So this would be something like this. Okay? Whereas if we did it in the opposite order, down, cross, left, so let's erase this for a second, so that we're talking about this now. What would we get? We would get into screen, or this. Down, curl your fingers, inward. So notice here that if we imagine taking this blue vector arrow and just taking the point at which it's based on the surface, imagine moving this to a new point. Then we get the vector sort of changing a little bit, and as we move this vector closer and closer, eventually this vector is going to point out of the screen. So in other words, if we choose this direction of to the right, that agrees with this orientation here. Because if we have an outward pointing vector here out of the screen, right, out of the screen, we could translate it or move it to here, and this normal vector here could continuously vary and change into this vector here. So that's how you want to do it. You basically want the right-hand rule to agree. You want to find the direction, either left or right, so that when you do this vector crossed with that direction, it should give you something that is comparable or compatible, let's say compatible to this normal vector here. Or if you want to think about it in the other way, that's very similar to Green's theorem. It does confuse some people though, harder for them to visualize here. If you imagine walking on this path right here, to your left, this is touching the top surface. Your right hand would be off the surface. So you could think about it like that. When you walk around the surface, you want your right hand to be off the surface, or your left hand on the surface. No matter how you do it, there's lots of equivalent ways to think about this, but that should be the orientation. So we'll go ahead and give that name del S. So let's go ahead and do the line integral portion of Stokes' theorem. We're going to do both sides. Let's start with the line integral side. So del S, the boundary of this, is the unit circle in the xy plane. So we can easily parameterize the unit circle in the xy plane, saying cosine t sine t 0 for t in the interval 0 to 2 pi. Okay? So then, the line integral around the boundary of S, f dot dr, would be the integral from 0 to 2 pi. We would do our replacement. So negative y, 2x, x plus z, dotted with the derivative of our parameterization, negative sine t, cosine t, 0, dt. So we should get sine squared of t plus 2 cosine squared t dt. Couple of ways you can do this integral, but it is fairly straightforward. Be aware that you can break off one of these two cosine squareds and group it with the sine squared, so you'd get 1 plus the cosine squared of t. Then you can use the half angle identity here to, yeah, half angle identity to complete this. If you go through those steps, you will get that the answer here is should be 3 pi. Okay, so that is the line integral version. Now for Stokes' theorem, we're going to go ahead and we're going to check now the surface integral approach. So for the surface integral approach, we have to parameterize the actual surface S itself, which is the upper hemisphere. So we can do this by using spherical coordinates. We've done this before. So this would be cosine u, sine v, sine u, sine v, cosine v for u comma v in, let's say, the domain D, which is 0 to 2 pi, run out of room here, crossed with 0 to pi over 2, right? This angle V, which is playing the role of phi, this angle here, we want to go to a maximum of a right angle, pi over 2. U, playing the role of theta, right? We want to go all the way around, so that's going to be 0 to 2 pi. So we want a normal vector that is pointing upward. We've done this before. The correct order to cross these in to produce an outward pointing normal vector on the upper hemisphere is the order RV cross RU, which is cosine u, sine squared v, sine u, sine squared v, comma, sine v, cosine v. Okay? We also need to calculate the curl of f. So the curl of f ends up being 0, negative 1, 3. So this would end up being the double integral over S, curl of f dot ds. This is equal to the double integral over d, which is 0, negative 1, 3. Now technically in this vector, we would, if there were an x in here, or maybe like a z, we would replace that z with, for instance, whatever z is on your parameterization. But because in this result, right, these are equal, there is no x, y, or z, there's nothing to replace. So we're not skipping a step, there's just nothing to do for that step because there is no x, y, or z. So then what we would do is dot it with our appropriate normal vector, which we found to be this. So cosine u, sine squared v, sine u, sine squared v, sine v, cosine v, dA, which will end up being du dv, depending on the order that we choose. So double integral over d, this would be negative sine u, sine squared v, plus 3 sine v, cosine v, dA. So now remember that our bounds for u are 0 to 2 pi. So u is in the domain 0 to 2 pi. So whenever you have an integral like this, and you notice that one of your bounds is a full period of sine or cosine, 0 to 2 pi, you're going to want to check out those integrals first. So for instance, in this term right here, the sine u, the integral from 0 to 2 pi of sine of u du is equal to 0. So this whole term is 0. It doesn't matter what the integral of sine squared of v is. We don't even have to think about calculating it, because whatever it is, whatever number it ends up being, whether it's 0 or something dramatically different, it's going to be multiplied by 0, and so in the end, the product is still 0. So we are selectively looking for the nicer, easier integrals to calculate, because there's a good chance that on this range, one full period, that the integral is 0. So that's 0. Now in this term, there is no u, so we know that the u integral here is really just 0 to 2 pi du, which is going to be 2 pi. So this will multiply by the 3 to give us a 6 pi. And then we'd have an integral from 0 to pi over 2 sine of v cosine of v dv. And we can use a u substitution here. W equals sine of v, dw is cosine of v dv. This does work. You end up getting 3 pi for the answer. So Stokes' theorem is verified. It does give us the correct answer no matter how we approach it. All right.